in today's lecture, what we'll start with is rocket propulsion. So after giving a little bit of basics from rocket propulsion, what we'll do is we'll move on to the questions from irodov. Okay. So let's start with rocket propulsion. Rocket propulsion. Okay. Now suppose a rocket. There is a rocket. Okay. And on the from the backside of the rocket, there is a gases coming out. And this gases is moving with velocity u. And this u velocity is given with respect to rocket. Okay. And suppose the rate of mass of gases that is coming out is given by dm by dt. dm by dt means 5 kg of gases is coming out per second. That means the first second 5 kg of gases came out. Okay. Then after that 5 kg of gases came out. After that 5 kg of gases came out. That means each second is passing, the rocket is ejecting 5 kg of gases from itself. Okay. dm by dt is nothing but amount of or mass of gases ejected per second. Understood? So dm by dt is nothing but mass of gases ejected per second. Okay, mass of gases ejected per second. And u out here, this u, okay, this u out here is nothing but the velocity of gases with respect to rocket. Velocity of gases with respect to rocket. Fair and fine. Okay. Now the force experienced by the rocket due to this propulsion is nothing but force is equals to dm by dt, or the rate of mass of gas flow rate or mass flow rate of gases into velocity of the gases with respect to rocket. Okay. Now one thing to note out here, if the gases are going in downward direction, the force experienced by the rocket would be in upward direction, force of propulsion. Understood? So if the gases are going in downward direction, the force will be exerted on the rocket in upward direction. So one thing to note out here, the force of propulsion is opposite to the velocity vector, isn't it? So I'll introduce a minus out here. Understood this much? So this is the main crux of the thing that I'm going to do out here. Now some of you might say, sir, how is this feasible, or how did you come to this conclusion? Okay. So you can come to this conclusion by using F is equals to dp by dt. Okay. But that approach will give you a very confused kind of concept kind of thing. Okay. Because you'll understand the difference between dp by dt and this kind of situation in upcoming problem. Okay. So the thing that I'm going to do is I'm going to take a sledge. Okay. And on this sledge, there is a mass m, delta m kept out here, and there's a person out here. Okay. The person and the sledge both weights capital M mass. Okay. Capital M mass. Understood? Now this entire system was moving with, let's say, v1 in this direction. Okay. Now what this person does is he picks up the stones and throws it. Okay. What will happen? Himself plus the sledge will accelerate in this direction or will increase the velocity in this direction, isn't it? That's what conservation of center of mass tells us, or conservation of momentum tells us, isn't it? If I pick up a stone, suppose this block plus this person, okay, and this mass delta m was kept. Okay. Now if this person picks up the mass and throws it, okay, what will happen? This entire system will accelerate or change its velocity in the left hand direction, isn't it? Okay. So initial momentum of the system was am plus delta m into v1 in left hand direction. And after this, what happened? A person, okay, this person, the same diagram I'm drawing, okay. Okay, this person throws the stone delta m with velocity u. Okay, understood? Out here, the person throws the stone with velocity u. Now the thing to note out here, this velocity is with respect to whom? See, if I pick up a stone, okay, if my capacity is 10 meter per second, okay, I'm throwing a stone with 10 meter per second, okay. Now it doesn't matter how fast am I moving in this direction, the stone I have pick up and throw will always be with respect to 10 meter per second. That velocity of stone would be with respect to me, no? Okay, I would see the stone moving away with 10 meter per second. Understood? And suppose after throwing the stone, what happened? Suppose it was moving with velocity v1 out here. Okay, me and the entire system would change my velocity to v2. That means what? If after I throw away something, what would happen? I would accelerate a little bit, or my velocity in this direction would increase a little bit. So initially, the entire thing was moving towards left with v1. Finally, what happened? After I threw away the stone, this velocity v2 or the entire system, okay, changes velocity to v2. Understood this much? Now the thing out here to note is this V1 and this V2 is with respect to someone sitting on the ground, whereas this U is with respect to someone on the sledge. Understood this much? Okay. Now when I have to apply conservation of momentum, I cannot directly use this velocity, no? Okay. I have to use the velocity with respect to ground. So how do I convert this velocity with respect to ground? This velocity minus velocity of the sledge. So if I'm picking up and throwing it, okay, with respect to me it's 10 meters per second. But with respect to someone sitting on the ground, what will happen? He'll see the stone move with u minus velocity of how much? Velocity of the sledge, isn't it? Okay, it's same like dropping a ball from a moving car or dropping anything from a moving vehicle. Understood? If I drop a ball from a moving vehicle, with respect to me it has zero initial velocity. Okay, but with respect to someone sitting on the ground, what will happen? The velocity of the car will be added to that ball. So similarly, same thing is happening out here. U is the velocity of the stone with respect to me. Okay, but with respect to someone sitting on the ground, what is happening? This velocity is nothing but u minus the velocity of the vehicle. The velocity of the vehicle is v1 out here. This much is understood. Now, after converting all my velocities to ground frame of reference, then I can apply conservation of momentum. Okay, so let me apply conservation of momentum. The entire human plus sledge has a mass m. The stone has a mass delta m. Okay, so initial momentum. Initial momentum, let's take this direction as positive. Okay, this direction as negative. So initial momentum is nothing but m plus delta m into v1. Okay, this is initial momentum. Initial momentum. And minus, that means it is going in backward direction. Okay, final momentum. Final momentum. When I'm writing the momentum, all my velocity should be from ground frame of reference. So final momentum is m v2 or minus mv2 plus delta m u minus v1. So final momentum is mass of the sledge plus mass of the human into minus v2, or I'm taking this minus outside. Okay, minus v2 plus delta m into u minus v1, isn't it? And since all my velocities out here are from the same frame of reference, isn't it? This momentum out here was from the ground frame of reference. This momentum out here was also from ground frame of reference. So since all my momentum are from ground frame of reference, I can simply apply conservation of momentum because no external force is acting on this mass plus stone system, isn't it? So I can apply conservation of momentum between this and this. So initial momentum is equals to final momentum. So minus m plus delta m v1 is equals to minus m v2, okay, plus delta m u minus v1. This much is done. Okay, what I did out here, listen to me again. Okay, the entire system, mass plus stone, was moving with velocity v1. The person picked up the stone and threw it with some velocity u. That velocity u is with respect to him. Okay, with respect to someone on the ground, what will happen? The velocity is u minus initial velocity or u minus v1, but u minus velocity of the vehicle, isn't it? So as soon as I converted the velocity in ground frame of reference, okay, I can apply conservation of momentum, isn't it? So whenever you're applying conservation of momentum or conservation of center of mass or displacement of center of mass, okay, always convert everything to same frame of reference. Okay, either to ground frame of reference or to the frame of reference of the slab. It's better if you convert it to ground frame of reference. Understood this much? So let me solve this equation. Okay, it would be minus m v1 minus delta m v1 is equals to minus m v2 plus delta m u minus delta m v1. Okay, see, minus delta m v1 and minus delta m v1 would get cancelled. Okay, these two got cancelled. So I'm left with equation. Now if I send this mv2, okay, to the right hand side, it would be mv2 minus mv1 is equals to delta m into u. Can I take m common out here? Okay, delta m is equals to v2 or m into v2 minus v1. Okay, is equals to delta m into u. Okay, what is v2 minus v1? v2 is nothing but the final velocity of the sledge plus human. v1 is nothing but the initial velocity of the sledge plus human. Okay, and what is v2 minus v1? v2 minus v1 is nothing but change in velocity of the sledge plus human system, isn't it? So I can write v2 minus v1 as delta v. See, v2 minus v1 is nothing but final velocity of the sledge minus initial velocity of the sledge, or I can write this as change in velocity of the sledge, isn't it? Okay, so I'm writing this as change in velocity of the sledge. Okay, understood. So let me derive this equation. M into delta V is equals to delta M into U. M into delta V is equals to delta M into U. Okay, understood this much? I was throwing this particle with velocity u. That u was with respect to me. That is me standing on the sledge. Okay. Now to convert that velocity in terms of ground, so that velocity plus the velocity of the frame or velocity of the sledge or velocity of the vehicle the stone was carrying, isn't it? So from conservation of momentum, I got this equation. Now let's say the entire process took delta t amount of time. Okay. Let's say 5 seconds or 2 seconds. Delta t amount of time or delta t is the time for entire process. Is the time for entire process. For entire process. Okay. That means this the act of me picking up a stone and throwing it at 10 meters per second. Let's say it takes 2 seconds. Okay. 2 seconds. And that is given by delta t. Okay. So suppose there are a lot of stones kept of delta m, delta m, delta m. Not only one stone, there are a lot of stones kept. Okay. 10 stones kept of delta m. Okay. And I take a mass and throw it with velocity 10 meters per second. So each time I'm throwing, okay, the delta V is changing by this much amount from V1 to V2. Then again I picked up the stone and threw it V2 to V3. Again I picked up a stone and threw it V3 to V4, isn't it? So each time I'm picking up a stone and throwing it, the velocity is changing, isn't it? Or delta V is there. Understood? So each time I'm picking up a stone and throwing it, the entire system increases its velocity in the opposite direction. Okay. Now suppose I make this step automatic. Automatic means every 2 seconds I'm throwing a stone with 10 meters per second. What will happen? This entire system will be a continuous process. Okay. So what happens if I divide delta t out here? Divided by delta t. Delta t. Delta t. Okay. That means what? I'm continuously picking up a stone and throwing it 10 meters per second. Okay. If you see properly out here, delta v by delta t is nothing but can be written as acceleration. Okay. Delta v by delta t is not exactly acceleration, it's dv by dt. But suppose I'm making the mass of the stone very small. Okay, and I'm doing it continuously. That means the time taken is also very small. That means what? I can write delta v by delta t as dv by dt. And dv by dt is nothing but the acceleration of the sledge in leftward direction. So this is nothing but acceleration. Okay. And if the dm is small and dt is also very small, then I can write this as dm by dt, isn't it? Dm by dt. So from this equation, I can say that mass of the sledge plus human is into acceleration is equals to dm by dt into u, where u was the velocity of the stone in that direction or velocity of the stone with respect to sledge in that direction, isn't it? Understood this much? And the thing to note out here, the direction of acceleration is opposite to the direction of velocity out here. So I'll introduce a minus dm by dt into u. That means if I'm throwing the stone in that direction, the sledge and the human will accelerate in this direction. Understood this much? And what is mass into acceleration? Mass into acceleration is nothing but force. Okay. So this entire system or mass into acceleration can be written as force or force of propulsion. Okay. So force of propulsion is given by minus dm by dt into u. Understood? So I put this situation out here. The thing to note out here is this u is given with respect to the vehicle. Okay. The direction of force is the direction of force is opposite to the direction of u. This much is understood. Fair and fine. Now you might have a question, sir. As I'm picking up the stone, I'm throwing it. Okay. Won't the mass of the system change? Okay. See, if I'm picking up the stone and throwing it, and I'm doing it continuously. Okay. This capital M is also supposed to change. The important assumption in rocket propulsion is the mass of the rocket or the mass of the system is so huge. Okay. That doesn't matter how much stones you keep on throwing, the mass M out here or the entire system doesn't get changed. Okay. That means this mass delta M is very small when compared to this capital M. Okay. That means even if I pick up 1,000 stones and throw it, the mass of this rocket is not changing. Okay. Understood? And what happened if the mass of the rocket was changing? I have to apply dm by dt. Okay. dm by dt means rate of change of mass of the system also. Okay. And in certain problems, we learn that rate of change of mass of the rocket is nothing but rate of change of ejection of gases. That means if I throw over 10 kg of stones, okay, the mass of the rocket will decrease by 10 kg only. Understood this much? Okay. So the important assumption out here is dm by dt, the rate of change of dm by dt is actually equals to rate of change of mass of or rate of change of mass ejection of these stones. Okay, that means rate of change of mass of the rocket is equal to rate of change of mass flow rate. Understood? That's why I haven't taken capital dm by dt, because it's adjusted out here. Okay, so using this concept, I'll solve this question. In this question, a rocket, okay, ejects a steady jet of gas whose velocity is u with relative to the rocket. So whenever rocket propulsion is coming up, no, all the velocity that is being ejected are with relative to the rocket or relative to the vehicle. Okay, so out here there is a rocket, and it is ejecting some gas with relative to rocket. Okay, okay. So force due to propulsion or force due to propulsion is how much? dm by dt into u. Force due to propulsion is nothing but dm by dt into u, but mu is nothing but the mass flow rate, isn't it? So out here mu is given as mass flow rate. So force of propulsion is mass flow rate. Sorry, force of propulsion is mass flow rate into velocity of ejection of gases. Okay. Okay. If the mass flow rate is in downward direction, force of propulsion would be in upward direction. The question is saying demonstrate that the rocket motion is, in this case, takes in the form of, we have to prove this equation, mass into acceleration. This is nothing but acceleration. Okay, mass into acceleration is equals to force minus mass flow rate into mu. Okay, where m is the mass, w is the acceleration, and f is the external force. Okay, so I got, so if the rocket is ejecting u amount of velocity, force of propulsion is nothing but dm by dt into u, or it can be written in the language of irodov as mu into u. Okay, now the question is asking, or question is telling, there is another additional external force acting on the rocket. Okay, then what would be the acceleration of this rocket? Understood? See, force due to propulsion is nothing but dm by dt into u or mu into u. Okay, if I add another external force, what is the acceleration of this rocket? Can I say net total force is equals to force of propulsion due to F external is equals to mass of the rocket into acceleration. Okay, so force of propulsion is nothing but mu into u or dm by dt into u. I can easily say that force external or mass into acceleration, I have to bring these terms up in these terms. Okay, mass into acceleration is equals to force minus mu into mu. Okay, so mass minus minus dm by dt. There was minus dm by dt mu. Okay, minus mu into mu. Why? Because the direction of force of propulsion will be opposite to the direction of velocity of ejection of gases. Okay, so out here F external minus mu into u is equals to mass into acceleration of the rocket. Understood? Okay, out here what I've done is I've simply taken up a concept, okay, of conservation of momentum. Okay, so if I'm throwing away a lot of stones, what will happen? The velocity of the sledge will keep on increasing, and I use that concept in deriving the equation of propulsive force. Okay, or force of propulsion. And after that, the question is simply asking if there is some velocity u ejected from the rocket. That means the force of propulsion is in opposite direction to the velocity with dm by dt into u. And if I add another external force, what is the total acceleration? Okay, so force of propulsion is nothing but mu into u. Okay, if I consider this direction as positive, this direction as negative, the force of propulsion is nothing but mass flow rate into velocity in the opposite direction. This negative is for the opposite direction, plus external force is equals to mass into acceleration. So I prove this scenario out here. Okay, but let me say it's not over. Okay, I need to discuss some more things out here. Okay, the thing that I'm going to discuss is this much you understood, that force of propulsion is equals to dm by dt into u, or force of propulsion is equals to minus dm by dt or mass flow rate into u, or velocity of gases with respect to rocket. Okay, let me write it. Dm by dt is nothing but mass flow rate, u is nothing but velocity of gases with respect to rocket. Okay, now the thing that I'm going to say out here will come repeatedly with negatives. Okay, question have been asked from them. Okay, now the problem with this kind of scenario is I don't know exactly. Suppose you have a pipe out here. Okay, suppose you have a pipe out here. Okay, okay, and gases are flowing out with some velocity u. Okay, with respect to the pipe. Fair and fine. Can you determine the mass flow rate, or can you weigh out the kg, or how much kg of gases is flowing out per second? No. Okay, but you can determine something. The volume of gases is, or volume of gases flowing out per minute. Okay, so what I'm trying to say out here is, how do I determine, okay, this dm by dt or mass flow rate from the area of the nozzle and velocity of the gases? Okay, see, suppose the area of the nozzle or area of the pipe was given as a. Okay, and suppose I'm calculating for delta t amount of time. For delta t amount of time. Okay, for delta t amount of time, what happens? Okay, how much volume of the gases was ejected? See, u into delta t. Suppose if this gas particle was out here at t is equals to 0 second. After delta t second, how much time it will go? It will go out to here, and this distance is nothing but u into delta t. So how much volume of gases in is there in this much amount of volume is nothing but a into u into delta t. Understood? The volume of gases that is there in this much amount of cylinder. Okay, this is nothing but cross sectional area into u into delta t. And this was the amount of gases ejected for delta t amount of time. No, suppose I'm stopping a clock for 1 second. Okay, I started my stopwatch and this particle was out here. At 1 second, this particle is out here. Okay, and it is continuously coming out. So forget that for a moment. So at 1 second, the particle is out. So all the gases are coming out, or all the gases are out here at 1 second. No, okay, and the remaining spaces are filled out by other gases from behind. Okay, if this gas came out here at 1 second, the gas behind it will fill this space, the gas behind it will fill this space, so the entire volume is filled, isn't it? Understood? So out here, amount of gases flowing, or volume of gas, volume of gas flowed out in delta t time, is nothing but how much? Area or volume of the cylinder, which is area into u into delta t. Area into u into delta t, where u into delta t is nothing but this length. Why? Because u is velocity of the gas and delta t is time for which it traveled, isn't it? So volume of gas flowed out in time delta t is equals to a into u into delta t. This much is understood. Okay. Now what is the mass of gas flowed out in the same time? Mass of gas flowed out in delta t time. In delta t time is what? What is the relation between mass and volume? Mass is equals to density into volume, isn't it? So mass of gas flows out in delta t time is nothing but density of the gas into volume, or AU delta T. But rho is nothing but density of the gas. Density of the gas. Okay. So mass flow rate. Okay. Mass flow rate is nothing but how much amount of, or how much volume of, or how much mass of gases is flowing out in delta T times. Okay. The amount of gases or the mass of gases flowing out in delta T time is nothing but mass flow rate. And volume flow rate is nothing but the volume of gases flowing out per delta T. Okay. So volume flow rate is how much? Total volume divided by time, or delta Q divided by volume divided by time. Volume divided by delta T, which is nothing but AU delta T by delta T. Let's change this as delta into small t, okay, in order to avoid confusion. So volume flow rate is nothing but A into delta U, or area of the nozzle, or area of the pipe, into velocity of the gases, or velocity of whatever liquid is coming out, isn't it? Similarly, mass flow rate. Okay, this is nothing known as mass flow rate. Okay, is nothing but mass coming out for delta time divided by delta t, which is nothing but density into area into u into delta t by delta t. Or mass flow rate is nothing but rho into a into u. Rho into a into u. Okay, out here u is nothing but velocity of the gases with respect to the nozzle, or with respect to the rocket, or with respect to whatever the vehicle that is carrying the gases. Okay, this u is not with respect to ground frame of reference. Understood this much? So mass flow rate is nothing but rho into a into u. Okay, now if I substitute this mass flow rate is nothing but dm by dt written out here, no? Okay, so if I substitute this mass flow rate as dm by dt as rho into a into u, force of propulsion, okay, is nothing but minus rho a u square. This minus signifies that the direction of force will be opposite to the direction of velocity of ejection. Understood this much? And this formula will be used again and again in fluid mechanics. Okay, in fluid mechanics, whenever rocket propulsion is there, okay, or the force imparted, this formula is going to be used again and again. Understood this much? Okay, so in your mechanics or in this chapter, most of the time dm by dt will be given. But once you're studying fluid mechanics, okay, the dm by dt value won't be given. Dm by dt is nothing but simply density of the gases into area of the nozzle, or area of the pipe, or cross-sectional area of the pipe the gases are coming out from, into velocity with respect to nozzle, or velocity with respect to rocket, or velocity with respect to the pipe. Okay, where rho is nothing but density of the fluid, a is nothing but the cross-sectional area, and u is nothing but the velocity of the gases. Understood? So these are our concepts that we are going to use later on. Okay, and one more interesting thing that I'll tell you. entire fluid, not fluid. Suppose you take up IT and you take up engineering, or suppose you take up rocket propulsions. Okay, they will use this formula. Okay, and one more modified form of Bernoulli's equation. Actually, it's known as Navier-Stokes equation. See, Bernoulli's equation is for frictionless fluid. So Navier-Stokes equation compensates the value of friction. Okay, so that Bernoulli's equation is plugged into a computer, and your entire, suppose some amount of explosion is happening out in rocket, what happens? The gases are exploded inside, okay, and thrown outside with the help of a nozzle. The entire design, okay, or the entire calculation takes place with the help of this formula. Understood? And one more formula, that's the Bernoulli's equation. So not Bernoulli's equation, it's known as Navier-Stokes equation. See, some of you might tell that we use Reynolds equation. Reynolds equation is so complex that we do not use it. We used naturally while studying engineering, we use Reynolds average Navier-Stokes equation. We don't use Reynolds equation directly. Okay, it's so complex that the computer. Little I'll tell you something. There was a professor in IT Kharagpur. Okay, the simulation for which he did. Okay, for Reynolds equation, it took him or it took the computer 2 days to bring out a picture, and this picture was this small. Actually, what he was simulating was how does a fire behave after 1 second or 2 seconds. Okay, that was the thing he was simulating. So you use modified form of Bernoulli's equation. Okay, a simpler form of Reynolds equation, which is also known as Navier-Stokes equation. And that itself is so complex that you have to use a computer to do it. Okay, sometimes you use codes, sometimes you use commercial software such as Analysis and okay, but that's later. Out here you only have to remember two formulas. Force of propulsion is equal to minus dm by dt into u. And in fluid mechanics, whenever you're studying fluid, force of propulsion is equal to density of fluid into area of the cross-sectional area of the nozzle into u, or relative velocity of the gases with respect to nozzle, relative velocity of the gases with respect to the rocket. This much is done. Okay, and now we'll move on to the next question. So what is the next question? Let's see. Okay, so in this question there was a rocket. Okay, the rocket was at rest initially. Okay, the initial mass of the rocket was m0. Okay, now what happened is the rocket started ejecting some gas, okay, with velocity u. And as soon as the rocket started ejecting the gases with velocity u, force of propulsion takes place. And this force of propulsion accelerates the rocket. So let's say acceleration will be in this direction. Okay, what is acceleration? Acceleration is nothing but the rate of change of velocity. So after a certain time, what will happen? The velocity of the rocket will increase. The question is asking, okay, this was the rocket. Initial velocity of the rocket was 0. The question is asking after time t, okay, there will be acceleration on the rocket, no? So acceleration of the rocket will increase the velocity of the rocket. So let's say at time t, the velocity of the rocket is v. Okay, and as the gases are being ejected out, the rocket is being lighter and lighter, isn't it? So the mass of the rocket will decrease. So the question is asking when the mass of the rocket is m, find out the velocity of the rocket. Okay, so we'll use the same concept out here, but a little bit of additional details will be given. Okay, so force of propulsion is equals to minus dm by dt into u, isn't it? Okay, force of propulsion is nothing but mass of the rocket. Let the capital M be mass of the rocket. Okay, into acceleration of the rocket. Capital M is nothing but the mass of the rocket into acceleration of the rocket. Okay, is equals to dm by dt into, okay, acceleration can be written as dv by dt. Okay, so I can write this same equation as m into dv by dt is equals to minus dm by dt into u. Now if you see this dm by dt question very carefully, what was this dm by dt? This was nothing but the rate of flow of gases, how much kilogram of gases was being ejected per second, or how much kg of gases was being expelled. Okay, now see what happens if I say the rate of ejection of gases is equals to the rate of mass decrease of rocket. Okay, that means inside the rocket, if I'm throwing away 5 kg of masses per second, okay, the mass of the rocket will decrease by 5 kg per second, isn't it? Suppose initially the entire liquid rocket plus everything was 100 kg. Okay, it is ejecting gases at 1 kg per second with certain velocity. Okay, now the rocket will also get lighter by 1 kg per second. No, at time t is equals to 1 second, rocket is 99 kg. At t is equals to 2 second, rocket weight is 98 kg, isn't it? So can I say this dm by dt is also rate of change of mass of rocket? So rate of change of ejection of rocket or ejection of gases is also equals to rate of change of mass of the rocket. Okay, rate or mass flow rate of gases, mass flow rate of gases is also equals to a rate of mass decrease or rate of change of mass of rocket. Change of mass of rocket. Okay, that means mass flow rate of the gases is also equals to rate of change of mass of the rocket. That means if I'm throwing out 5 kg of masses per second, the rocket will also get lighter by 5 kg per second. So this dm by dt or small dm by dt can also be written as capital dm by dt, isn't it? So this dm by dt can be written as d capital M by dt. Okay, and now when we see the equation, m dv by dt is equals to minus dm by dt into u. Okay, dt and dt gets cancelled. So out here am dv is equals to minus dm into u. Okay, and this u is constant. Okay, the relative velocity of the gases with respect to rocket will never change. Doesn't matter how fast the rocket is moving. Okay, because the capacity of the rocket is constant. No, if my hand has a strength of throwing a stone in 5 meters per second, doesn't matter how fast I am moving in backward direction, I can always just throw the stone in 5 meters per second with respect to my hand or with respect to me. Okay, and this u is nothing but velocity of gases with respect to the rocket. Now let's see the equation. So dv is equals to minus u dm by m. Out here u is nothing but a constant. I already explained to why. Because the capacity of the rocket will remain same. Because my capacity of throwing a stone with certain velocity will remain same. Doesn't matter how fast am I moving in this direction, isn't it? Okay. So when I integrate both sides, initial mass was m naught, final mass is m. Initial velocity was 0, final velocity is v. So when I solve this one, v minus 0 is equals to minus u ln m. Okay, from initial velocity of initial mass of m to final mass of m, or v is equals to minus u ln, or let me write this neatly in the next page. Okay, solve the equation. Let me just rewrite the solution, or if we, let me write it out here. Okay, v is equals to minus u ln small m by m naught. Okay, so this is the answer to our question. Now this is the same question as before. Okay, in this question the rocket is there. Okay, and it is ejecting some gases with velocity u, and this ejection causes an propulsive force. This force, okay, causes an acceleration in the rocket, and this acceleration is given by w. In the question it says that acceleration out here, okay, is constant. This acceleration of the rocket is constant. Okay, we have to find out the mass of the rocket with respect to time. That means as time is going on, what is happening? The velocity of these gases are being ejected and ejected, so the rocket will get lighter and lighter. So if the initial mass of the rocket was equals to m naught, what is the final mass of the rocket? Okay, so you can simply say force of propulsion is equals to minus dm by dt into u. Okay, force of propulsion can also be written as mass of the rocket into acceleration of the rocket. Acceleration of the rocket is written as w in irodov. Okay, don't be confused of that. Is equals to minus dm by dt into u. Okay, and I have already said that dm by dt, or rate of change of or mass flow rate of gases, is also equals to w d capital M by dt. No, dm by dt is also equals to d capital M by dt. Or rate of mass flow rate of gases is also equals to rate of decrease of mass of the rocket, isn't it? So this dm by dt will be substituted by capital dm by dt. Capital dm by dt. Now what I have to do? Now simple. W is constant. Okay. Or let's change this dt. Okay, to the left and m to the right. So w dt is equals to minus u dm by m, minus u dm by capital M. Now if I integrate both sides, from time t is equals to 0 to time t is equals to t, at time t is equals to 0, mass was equals to m naught. At final time I have to find out the mass, or w into t is equals to minus u ln m, the lower limit and upper limit are m and m naught. So this will be nothing but wt is equals to minus u ln m by m naught. If I send this u to the left hand side, what will happen? Wt by u, or minus wt by u. I'm also sending the minus to the left hand side. Okay, so this is the equation that I get. I have to find out the value of m with respect to time. No? So let's do one thing. Let's take e in both sides. E to the power minus wt by m is equal to m by m naught. This is nothing but just mathematics. E to the power minus wt by u is equal to m by m naught. Or out here, can I write the final answer as m, the final mass of the rocket, is equals to m naught e to the power minus acceleration into time by e. So this is the answer that we get. Okay, then fine. So in this question, we need the same type of concept but with a different twist. Okay, so in this question, there is a rocket out here, and the rocket is moving with v naught. Okay, now instead of ejecting the gases from that direction, the nozzle is fitted in sidewise twist. Okay, and the gases are escaping in the side direction with velocity u. So in which direction is the propulsive force? The propulsive force would act in downward direction, no? So force of propulsion is acting in downward direction. Fair and fine. Okay. Now, where have you seen this kind of motion? Where the force is perpendicular to the velocity? Circular motion. In circular motion, the force is always perpendicular to the velocity, no? So suppose I draw the rocket out here. Okay, I've drawn the rocket very small. Okay. Initial velocity v naught. The force is acting in this direction. And the force will always be perpendicular to the velocity, no? What kind of motion would it execute? A circular motion. Okay. Now the question is asking, suppose the rocket travel for time t. The rocket traveled for time t. Okay. So after traveling for time t, the rocket reached out here. Out here. Moving with velocity v naught. Why? Because the force is always perpendicular to the direction of velocity. So it will never change the magnitude of the velocity. And in this direction is the propulsive force. The question is asking, find out the value of angle alpha through which it moved. Okay. So the first intuition I get by seeing this question is I must apply the equation of circular motion, where force or propulsive force is equals to mass into centripetal acceleration. Propulsive force is given by minus u d capital M by dt. Okay. I can also use small m by dt. Okay. I can also use d capital M by dt. Both are of equal values, but out here I'm using d capital M by dt because I need to integrate with this mass. Okay. I'm concerned about the mass of this rocket. Understood? And I've already told you the rate of mass flow rate of gases is equal to rate at which the mass of the rocket is decreasing, isn't it? So out here, centripetal acceleration is nothing but v naught square by r. So if I rewrite this equation, I'll get minus u dm by dt is equals to am into v naught square by r. Okay, can I send this m to the left and dt to the right? So if I do that one, I'll get minus u dm by m would be nothing but v naught square by r into dt. I can integrate both sides. At t is equals to 0, m is equals to m naught. At t is equals to capital T, m is equals to m. Okay. Or minus u ln m from m is equals to small m to m naught is equals to v naught square by r into t from 0 to time t. Okay. I can rewrite this equation as minus u ln m by m naught is equals to v naught square by r into t. So from this equation I can get no r is equals to v naught square t divided by minus u ln m by m naught. I might ask, sir, we have asked to find the value of alpha. What are we doing with r? Out here, r is nothing but the radius of the circular path. Okay. Now see, if the velocity of the rocket is constant, what is the length of the path traveled? The length of the path traveled is nothing but v naught into t. The length of the path that is traveled is nothing but v naught into t. L is equals to v naught into t. And this L, or the length of path traveled, is also r into alpha, is equals to r into alpha. And from the equation of r, I can see that, or I can get the intuition that somewhere v naught and t somewhat would get cancelled. Okay. That's why instead of directly going for r, I have found out the value of r. Okay. And from these two equations, while v naught into t, v naught into t is equals to r. What is the value of r? The value of r is nothing but v naught square t divided by minus u ln m by m naught is equals to r minus u ln m by m naught into alpha, isn't it? Now to find out the value of alpha, let's cancel out v naught square t and t. So alpha is equals to minus u ln m by m naught divided by v naught is equals to alpha. Okay. Now see this minus. Okay. Minus of ln1. This minus. I can multiply inside the log. No. So if I multiply this minus inside the log, okay, it will be ln m by m naught to the power minus 1, and m by m naught to the power minus 1 is nothing but m naught by m naught by m. So this is our answer. Alpha is equals to velocity of ejection of gases. Alpha is equals to velocity of ejection of gases into ln initial mass divided by final mass divided by v naught. So this was our answer. Now what we'll study is acceleration with variable masses. Okay. Acceleration of bodies with variable masses. variable masses. Okay. So we'll first analyze the situation that is going on out here, and then I'll try to do that. Okay. So the situation that we are going to analyze is, suppose a body was there, okay, of mass m. It is pulled by a constant force A. The force out here is constant. Okay. What will happen? The acceleration will be developed, and the value of this acceleration is constant. And the relation between force, mass, and acceleration is given by force is equal to mass into acceleration. But what would happen if some amount of masses are leaked out from out here? Okay. Or what would happen if some amount of masses are continuously added out here? How do you solve this kind of question? Okay. So this is the thing that you're going to learn out here. Right. So before learning these things, let's go back to the basics. Okay. Let's forget about variable masses. Just tell me one thing. Okay. Suppose a block is out here. Okay. It is with zero velocity. This block of mass capital M. Okay. Is with zero velocities. Now a stone is kept out here. Stone is just hanged out here. Right there. Okay. Both the systems are with zero velocity. Now if the stone is dropped, okay, somehow the adhesive becomes loose and the stone is dropped. Will the block start moving in any direction? No, isn't it? So the block will not start moving. Similarly, suppose a oil tanker was kept. Okay, instead of a mass, a oil tanker was kept. Okay, and I somehow punched a hole out here, and oil started gushing out. Okay, so obviously there would be a propulsive force in upward direction, but I'm not interested in force in upward direction. Okay, I'm just analyzing the forces and motion in this direction or horizontal direction. So suppose the oil starts gushing out in this direction. Will this block move in any direction, right or left? No, the block will stay as it is. So I can safely deduce that if the masses or if loss of mass takes place from an object, the change in velocity doesn't take place. Okay, the velocity of the body doesn't change. So similarly, if this body was initially moving with v, okay, and after that I punched a hole and oil starts gushing out, what will happen? The trailer will keep or the block will keep moving with velocity v, isn't it? That's what's supposed to happen. Okay. Now imagine a scenario where I applied a force to it. That means out here, a oil tanker is kept. Okay, this oil tanker is kept of mass m plus let's say a little bit of oil, or let's say I applied a force out here. What would happen? This tanker would experience a constant acceleration, isn't it? Now if I punch a hole out here and oil starts gushing out, okay, what would happen to the acceleration? The acceleration would increase its value. See something. Suppose I'm pulling a van. Okay, a van is loaded with lots of sand, and I have a fixed capacity of 10 Newton. Okay, so I'm pulling it. Now somebody saw me struggle. Okay, and what he decided to do was he decided to lift off the mass, or he decided to lift off the sand. So what will happen? The block will accelerate faster, no? And why is that? Because the same amount of force is used to pull lesser amount of mass, so the acceleration will be much more, isn't it? This much you have understood. And suppose the opposite scenario happens. There's an empty oil tanker. Okay, I'm pulling with some force. Okay, and somehow somebody started to prepare or pour in lots of oil. Okay, lots of oil, and the oil started getting filled. What would happen to the acceleration of it? The acceleration will increase and decrease. That means what? I'm pulling a van and somebody is adding a sand on top of that. That means what? The van is getting heavy. So my acceleration will decrease, no? Because my capacity is 10 Newton, my capacity is same. But as the time goes on, I'm pulling much more heavier material, isn't it? So what we are going to do is we are going to analyze these two kind of scenario in this chapter or in this lecture. Okay, fair and fine. Now out here, okay, let's say we are going to analyze this scenario. Now, to analyze this scenario, the thing you have to understand about acceleration is what does acceleration do? What is the sole objective of acceleration? It changes the velocity vector, isn't it? So suppose this mass m, okay, was moving with velocity v. After time t, due to acceleration, what will happen? The velocity of this block would increase. Okay, so instead of dealing this scenario as a continuous process, we'll deal this scenario as a discrete process. That means process in time intervals. Okay, so instead of pulling continuously 10 Newton of force, what I'll do is I'll pull it in jolts. 10 Newton for 1 second, stop. Again another 10 Newton for 2 seconds, stop. Another 10 Newton for 3 seconds. Means I'm pulling the 10 Newton at 1 second interval and stopping it. So we'll analyze this scenario in that kind of process. Okay, instead of continuously pulling with 10 Newton, for the first second I pull it 10 Newton, stop. Then from t is equals to 1 to t is equals to 2 seconds, I can pull it 10 Newton, stop. Again from t is equals to 2 to t is equals to 3 seconds, I pulled with 10 Newton, then again stop. So I'll be analyzing in that kind of situation. Understood this one? Okay. So let's say for the time frame, for the time interval dt or delta t. Delta t can be 1 second, delta t can be 2 seconds, delta t can be 3 seconds, any second. But instead of continuously pulling it, I'm just jolting it. Okay, 10 seconds, 10 Newton for 1 second, stop, 10 Newton for another second, stop, 10 Newton for third second, stop. Okay, so what would happen? See, at time t is equals to 0, suppose the cart has some velocity v. Okay, at time t is equals to delta t, what would happen? The velocity of the cart would increase. At time t is equals to how much? Delta t or 0 plus delta t. Time t is equals to 0 plus delta t or delta t. Okay, the same mass. Okay, the same force out here, the force is constant. This force is constant. All the forces that I'm applying out here are constant. Okay, so the velocity of the body would become v plus some additional velocity dv, isn't it? Understood? Now if I have to analyze this scenario, okay, for what amount of time the force was applied? For delta t amount of time. And what is force into delta t? Force into delta t is nothing but the impulse applied on this car. Okay, and what is the formula for impulse? F into dt, isn't it? And impulse is nothing but change in momentum or final momentum minus initial momentum. Okay, so out here, if I analyze it, what is the impulse that I applied? Force for time delta t, isn't it? What is the final momentum? Final momentum is nothing but mass into final velocity v plus dv. So mass into v plus dv. Okay, what is the initial momentum? Initial momentum is nothing but mass into v minus mass into v. So what I simply said out here is impulse, okay, or force into dt is equals to final momentum minus initial momentum. This is what I've written, isn't it? Okay, and this final momentum minus initial momentum, f into dt, is equals to final momentum minus initial momentum. This final momentum minus initial momentum can be written as del t or change in momentum. So this can be written as change in momentum. Or if I analyze this, force is equals to dp by delta t. Okay, or force is equals to changing momentum divided by changing time. And when this changing momentum and changing time, when the time frame is so small, we make this delta t into dt and delta p into dp. So this was the Newton's law. Fair and fine. Now what happens if the mass is constant out here? See, okay. So I'll just erase this one. So if I solve this equation, f delta t, if the mass is constant, I'll get mv plus m into delta v minus mv. Okay, mv and mv gets cancelled, or f into delta t is equals to m delta v by, or m delta v. Delta t can go down out here. And when the time frame is small, this delta t can be written as dt, and this delta v can be written as dv. And dv by dt is nothing but acceleration. dv by dt is nothing but acceleration. So we get force is equals to mass into acceleration. Understood this scenario? Okay. So impulse is equals to final momentum minus initial momentum. Okay, it's nothing but a simplified form of, not simplified, I'm analyzing the same Newton's laws of motion, but from the perspective of discrete intervals. That means instead of taking force as a continuous kind of thing, I'm taking force for 1 second, then force for another second, then force for third second, and so on. Understood? So after this, I'll analyze this two scenario. Okay, so you get the idea out here. The gist out here is whenever variable masses are there, I have to apply this concept. Impulse or f dt or force that acts for delta time is equals to final momentum minus initial momentum. Okay, now let's take this first scenario when masses are subtracted, or when mass is subtracted. Okay, when mass is subtracted. And the second case is when mass is added. When mass is added. Fine. So when mass is subtracted, what happens is, I'll just draw this same scenario somewhat like this. Okay, a block. Okay, let's say it was initially moving with velocity v. Okay, and it was filled with oil. The entire mass of the oil plus tanker system was m. Now, without applying any force, if I just poke a hole and oil starts gushing up, will the velocity change? No, isn't it? Because force is required, or acceleration is required to change the velocity. That means force is required to give an acceleration. Understood? So without force, the velocity of this block won't be changing. Understood? Just imagine if the block was still. Okay, I just poked a hole and oil started gushing up. Does it move in any direction? No. So it was usually moving with v, and if I poked a hole, it won't start moving faster or slower. No. So to change the velocity, I need an force. To change the velocity, there must be acceleration, and to give some acceleration, there must be some force. This much is understood. Fair and fine. Now what happened is I applied some force. Okay, at t is equals to 0, I applied some force, and at the same time I poked a hole out here. Okay, I poked a hole out here, and oil started gushing out at the rate of, or at the mass flow rate of dm by dt, or delta m by dt, delta m by dt. That means per second, okay, delta m of fluid will come out of this, right? Or delta m of fluid will come out of this vessel. So I'll analyze this after t seconds. Okay, at t is equals to 0, I started the system. At t is equals to delta t, okay, I'll analyze the system. So at t is equals to 0, when I started the system, okay, this dm by dt I'll give as mass flow rate as dm by dt, or mass flow rate, mass flow rate is equals to dm by dt. Okay, I'll write it as me. Understood? Okay, that means per unit of time, this much kg of masses are coming out. So when I started, when I poked a hole and applied some force, what happened? Dm, or delta m amount of mass, is just coming out, and this delta m amount of mass is also moving with velocity v. No, it just started to come out. So to attain the velocity of the vehicle, it was in, isn't it? Now see, I also applied a force, okay, and this force was acting on the container. Okay, so my question out here is, will this force change the velocity of this dm mass? Just imagine, suppose you are accelerating in a car. Okay, the car is going with acceleration, not constant velocity, with means with acceleration. That means the speed of the car is increasing, and you throw a stone out of the car. Okay, the velocity of the stone with respect to someone on the ground will be the last at the moment, means when you throw out the stone, or the velocity of the car at the moment when you throw out the stone. But after that, what? The car changes velocity. Will the stone also change its velocity? No, because the stone was not in contact with the car, isn't it? So similarly out here, this mass, or delta m, will have an initial velocity of v, because it was ejected out when the velocity of the container was v. But will it change its velocity? No, because this force is not applied on out here, isn't it? So after delta time t, okay, after delta time t, what happened is, this mass, or the container, okay. Now what is the amount of masses left out here? See, the total initial mass was m, delta m of mass came out. So the remaining mass is m minus delta m, isn't it? And delta m is out here. Understood? Okay. Actually, this delta m was part of the initial mass. That means this delta m was part of the initial mass. That means if you want to see by equation, m minus delta m plus delta m. But don't go by equation. That means the entire delta m plus mass was constant out here. That means it was stuck together. Okay. And this total mass of the particle was, if you want to see by equation, I can take this as m minus delta m. Okay. But don't go it by that way. The total initial mass was m. After delta m mass came out, the final mass became m minus delta m. Understood this much? Okay. So instead of doing that like this, I'll say the total initial mass was m. Okay. And finally, what happened is, delta m is moving with velocity v, because delta m, or delta m, experiences no force. Okay. So instead of writing it out here, I'll write it out. Okay. Now a constant force was applied, and due to this constant force, acceleration happened. And what is acceleration? Changing velocity. So if this force was applied for delta t amount of time, the initial velocity was v. The final velocity is v plus delta v. But delta v is nothing but the increasing velocity. Understood this much? And this v plus delta v, this delta v won't be applied on this dm mass. Why? Because as soon as it got out of the vehicle or cart or whatever the container was, there was no force acting on this delta m mass. No. So this delta m mass would move with constant velocity, whereas some force was acting on this container. So the velocity of this container would increase. Understood? So this was the initial momentum, this was the final momentum. What is the total impulse applied? F into dt, because this changing velocity was for delta t amount of time. No. So if I analyze out here, impulse is equals to final momentum minus initial momentum, or f dt. F dt is equals to, what is the final momentum? Final momentum is nothing but m into v plus delta v. Sorry, m minus delta m. Okay, the remaining mass of the container into v plus delta v, into v plus delta v. Okay, plus I have to take the momentum of this also, no, because even this is moving with v. Okay, plus delta m v. Understood this much? This is the final momentum. What is the initial momentum? M into v. So minus m into v. Okay, so this is our equation. Fair and fine. Now when we analyze this situation, instead of taking dt, I'll take delta t. Okay, delta t. So af into delta t is nothing but, let me multiply these two terms, mv plus m into delta v plus minus m delta mv minus delta m delta v. Okay, so mv plus m delta v, I'm just multiplying the four terms, minus delta mv minus delta m delta v. Okay, And out here, plus delta mv minus mv, plus delta mv minus mv. Okay, so out here, okay, so f delta t, anything that can be cancelled here, this one and this one can also be cancelled. Okay, now an important assumption that I have to take out here is delta m into delta v is very small, so this will be nearly equals to 0. Okay, so f into delta t would be nothing but m into delta v. Okay, and f is equals to m. Acha, before writing f is equals to m into delta v, one thing to observe out here, this m out here is a variable quantity. That means as I'm going, okay, as the time is increasing, this mass is decreasing and decreasing, isn't it? So if the mass is decreasing, suppose I say after time delta t, how much of the mass is decreasing? Okay, it is nothing but m minus dm by dt into t. See, you didn't understand. Okay, if the mass flow rate is 5 kg per second, okay, the mass flow rate is 5 kg per second. That means 5 kg of oil is flowing out per second. Fair and fine. So if 5 kg of oil is flowing out per second, if the initial mass of the entire container plus fluid was 100 kg, what was the mass of the container after 3 seconds? M minus mu into T. That means 100 minus 5 into 3, isn't it? So the mass of the container at time T would be how much? M minus mu into T, or M minus mass flow rate into time T. So this mass is nothing but a variable quantity that can be written as M, or M minus mass flow rate into time T. Okay. So out here, when you analyze this, force into delta T is equals to M minus mu T, okay, into delta V. So let me write this quickly. Force into delta T is equals to M minus mu T into delta V. Okay. So this is the equation when the container is losing mass. Okay. Obviously, there is a propulsive force. The mass is ejected. Obviously, there is a propulsive force in upward direction. But I'm not concerned about the motion in this direction. I'm concerned about what happens when it moves or loses mass and moves in this direction. Okay. The thing to remember is for acceleration to happen, the force should be necessary. Okay. There should be a necessary force to accelerate the body. Okay. The thing out here is, the important thing out here is, if the mass is decreasing, the acceleration is increasing and increasing, or going on increasing. So we'll analyze that situation by this formula, or impulse is equal to final momentum minus initial momentum. This much is clear. Okay, so we get the equation F into delta T is equals to, or you get this equation F into delta T is equals to M minus mu T into delta T. Now what happens if a container initially of mass M, okay, an empty container initially of mass M, okay, initially of mass M is filled up with fluid with mass flow rate of mu, or mass flow rate mu is given by dm by dt. That means the empty container was of mass m, okay, and it was pulling it with force F, and someone opened a tap in which oil started flowing out with a flow rate of dm by dt. Okay, so we'll analyze this same scenario by the same principle. So after t is equals to 0, the cart was empty, the tanker was empty, and initial mass was capital M. So after time t, okay, at time t is equals to delta t, at time t is equals to delta t. That means delta t time has increased. Okay, and initially it was moving with velocity v. Okay, initially it was moving with velocity v. See, without force the velocity won't be changing. Doesn't matter you add mass and you remove mass. Okay, if you add a lot of mass provided, see, provided that mass, okay, that mass flow rate could have the same horizontal velocity as this container. Okay, so it doesn't matter you add mass or subtract mass, if there is no force, there is no changing velocity. Understood? Okay, now what is happening is, at time t is equals to delta t, what is happening? The container, okay, got filled with m plus mu into delta t amount of mass. Okay, and let's say that mass is delta m. Okay, after time t, the container or delta m amount of mass was added into this container. So out here, delta amount of mass was dropping. Delta m amount of mass was dropping out here. Okay, and at delta time t, the mass increased to m plus delta m. The force is nothing but the same value, F. Okay, and since force was there, okay, since force was there, there will be change in velocity. Okay, let the final velocity be v plus dv, where dv is the increase in velocity. Understood? Now if I add the same equation out here, impulse is equals to final momentum minus initial momentum, what do I get? What is the value of impulse? Let's draw a boundary out here. Okay, what is impulse out here? F into delta t, or F into delta t. What is the final momentum? Mass into final velocity, or m plus delta m into v plus delta v, or m plus delta m into v plus delta v. Okay, fine. What is the initial momentum? In initial momentum, the mass of the vehicle or the shell, or not the shell, the container, was velocity. What is the mass of the delta m? The mass of the delta m was zero, no? It was dropping from a tap, isn't it? So the horizontal velocity of this delta m mass was equal to zero, no? Isn't it? There was no horizontal velocity of this delta m mass. So initially, okay, this mass, okay, this mass of the container was moving with velocity v. The delta m mass was moving with zero velocity. That means the horizontal direction of velocity of this delta m mass was zero. Okay, so minus initial momentum is nothing but m into v. Okay, understood. Now if I analyze the equation out here, or if I rectify the equation, f into delta t, if I multiply this or if I expand this term, there is nothing but m into v plus m into delta v plus delta m v plus delta m delta v minus capital M V, minus capital M V out here. This capital M V and this capital M V gets cancelled, or f into delta t is equals to m delta v plus delta m v plus delta m delta v. Okay, and this is equals to 0, because delta m and delta v are very small, so when you multiply very small numbers, it becomes 0. So I get my equation f into delta t is equals to m dv m delta v plus delta m v. Okay, so this is my equation when I get, or when the masses are added. Now the same condition, see, this mass out here is a variable quantity. That means at time t, what is the final mass of this object? If the mass flow rate is mu, okay, at time t, how much mass would get added? Suppose initial mass of the container was 100 kg. Okay, 5 kg per second of oil was added to this container. After 3 seconds, what would be the total mass? Initial mass plus 5 into 3, that means 115 kg. So m plus mu into delta t. Understood? Sorry, mu into t. Okay. So at this mass out here is a variable quantity which has nothing but m plus mu into t. Understood this much? Okay. Now when I analyze the situation, or force into delta t is equals to m plus mu t into delta v plus delta m. This much should be understood by yourself. Now you must notice, see, now let me just underline the equation, then I'll tell you the few difference that you are noticing on it. Okay, this is underlined. Okay. Now the few difference that you are noticing out here. The equation when masses are added as in this manner. Okay, but the equation when masses are subtracted are in this manner. Why is that disparity? Or why is this disparity between two similar looking type of pieces? See, when masses are subtracted, no, the mass or delta m that was going out is losing its velocity. This impulse, okay, is not increasing the velocity of this elemental mass by delta v, no, isn't it? The entire impulse F into dt was used to not increase the velocity of this elemental mass by dv amount, isn't it? Whereas in this case, okay, the entire impulse, okay, was used to increase the mass of this delta m from 0 to v plus delta v. Okay, initially this drop of particle was not moving with velocity v in this direction. Initially the horizontal velocity or horizontal velocity of this particle was 0. Understood? That's why this is this. That's why this disparity of equation comes out of it. Understood? Okay. If this mass delta M was moving with delta V before being added to the container, okay, we have the same kind of equation out here and now. Understood the scenario? Okay. So whenever masses are being subtracted or added, just apply impulse is equals to final momentum of the entire system minus initial momentum of the entire system. Okay. Impulse is equals to final momentum of the entire system minus initial momentum of the entire system. And using these two equations, I'll just solve the next two problems. Now see, we'll use the formula that we have applied before or we have derived before to solve this kind of problem. Okay. Out here the question is saying a sand cart was loaded with sand. The entire mass of the system was M. A constant force was applied to it. Okay. And the sand started leaking at the rate of mu. And mu is equals to dm by dt, or mu kg per second. Okay. Find the acceleration and the velocity of the cart at moment t. Okay. So what is the equation that you're going to use? We're going to use this equation. Okay. So out here, when the sand is being ejected, okay, out here, this is the equation, isn't it? Let's copy this equation. See, the fundamental crux of this equation or of this principle is impulse or force into delta time is equals to final momentum minus initial momentum. Or impulse applied to the system is equals to final momentum of the system minus initial momentum of the system. We applied conservation of energy, no? Sorry, conservation of momentum, no? In collision. Okay. In the collision, the total impulse applied on the system was equals to 0. That's why final momentum was equals to initial momentum. Understood? So I'll just copy this equation, okay, and write it out here. So we are going to use this equation, okay. But f into delta t is equals to m minus mu t into delta b, or f into delta t is equals to m minus mu t into delta b. So for a very small amount of delta t, that means this becomes f dt is equals to m minus mu t into dv, isn't it? And what do you have to find? You have to find out the velocity and the acceleration. Okay. So first we'll start with velocity. So velocity of the cart is nothing but, if I rewrite this equation, if I send this term m minus mu t out here, so f dt by m by m minus mu t is equals to dv, isn't it? Out here the force is constant. Okay. Now I'll integrate this entire thing by, or integrate left hand side and right hand side by integration. The limits out here would be from 0 to v. The limits out here would be from t is equals to 0 to t is equals to small t. Okay. What was the initial velocity? And it's the initial moment, the initial velocity was equals to 0. Okay. Understood? So the initial velocity out here was equals to 0. Okay. So when I integrate from 0 to v, I'll get the same thing. If the initial velocity was anything other than 0, we would put the terms, that other term v1 out here. Okay. So how do I integrate this? Integration by substitution. M minus mu t is equals to x, or this is nothing but I'm following a mathematical integration by substitution. Okay, this is nothing but integration by substitution. M minus mu dt is equals to x, so I can easily write down dx by dt. Dx by dt is equals to minus mu. Okay, or out here dt is equals to minus dx by mu. So I substitute the value of dt. F, or out here I'll write down the equation f into dt. What is the value of dt? Minus dx by mu. So minus dx by mu. Okay. What is the value of m minus mu t? The value of m minus mu t was nothing but x. Okay. Is equals to dv. Okay. Let's just rearrange this term. Okay. Let me write the mu outside and x inside. Mu outside and x inside. Let me also send this minus to outside. Okay. Let me write this little bit neatly. Minus f by u dx by x. So minus f by mu dx by x. Okay. And this is nothing but dv. Integration of dx by x is nothing but ln x. So I'll get minus f by mu ln x is equals to v, isn't it? What is the value of ln x, or what is the value of x? So minus f by mu into the value of x is nothing but, the value of x is nothing but m minus mu t. So ln m minus mu t. Okay. And the final limits and lower limits of t is 0, upper limit of t is t, is equals to v. The lower limit of velocity is 0, upper limit of velocity is v. Okay. So if I put, it is nothing but minus f by mu. Okay. Ln m minus mu t. M minus mu t minus ln m minus mu into 0, which is ln m. Okay. And is equals to v minus 0 is equals to v. Now if I see this scenario, ln a minus ln b can be written as ln a by b. So m minus mu t divided by m, this entire term can be written as m minus mu t divided by m. So m minus mu t divided by m. M minus mu t divided by m. So this is our entire scenario. So v is equals to this equation. Okay, this is the value of v. You can also multiply this minus into inside and it will become m by m minus ut. So that doesn't matter out. We find out the value of velocity. Okay, the value of velocity is found out. Now what you have to do? You have to find out the value of acceleration, isn't it? And how do I find out acceleration from velocity? A is equals to dt by dt. Okay, so this entire thing minus f by u is constant. How do I write a? Or if I solve this out here, let's solve this out here. Okay, I got this equation. Let's see the equation that I got. This was the equation that I got. Select. This was the equation that I got. Let's put this equation out here, and it is the unnecessary part. This was the equation I got. Okay, the equation of velocity was given by this value. Okay, how do I find out acceleration? Acceleration is nothing but dv by dt. So I have to differentiate this entire term with respect to dt. So it will be nothing but minus f by mu into ln. Differentiation of ln is nothing but how much? See, this can be written as m minus mu t divided by m, can be written as 1 minus mu t by m, 1 minus mu t by capital M. So when I differentiate this, it would be nothing but 1 by 1 minus mu t by m, okay, into minus mu by m. to minus mu by m. I'm just applying chain rule is equals to acceleration. I differentiate this entire term with respect to t and I get this one. Okay. So this minus would get multiplied with this minus and this mu would get annihilated with this mu. So we're left with a by 1 minus mu t by m, okay, is equals to or into 1 by m into 1 by m is equals to a. I can take the LCM out here. It would be m minus mu t by m. Okay, this m can be sent out here, and this m can get cancelled. Okay, so acceleration at time t is nothing but a minus a by m minus mu t is equals to acceleration. Okay, and if you send this entire thing, no, you can analyze this entire thing by another process also. See, I get that force is equals to m minus mu t into a. This is the acceleration that I got. Now see, if I reverse analyze it, reverse analysis it means suppose this block was there. Okay, it was applied a force F. It was losing mass with mu into t, or let's say mu, or mu was the mass flow rate, or 5 kg per second, 6 kg per second. Okay, this was the acceleration. What do I know? Force is equals to mass into acceleration. Force is equals to mass into acceleration. Out here, what was constant? Force was constant. Okay, so if mass increases, the acceleration would decrease, and if mass decreases, the acceleration would increase. Okay, imagine something. I'm pulling a block, or I'm pulling 10 kg. Okay, I'm pulling a van with a constant force of 10 kg. Someone is removing the sand from the van. What would happen? The acceleration of the van would increase. No? The same thing is happening out here. Now, if m is a variable, which is nothing but m minus mu into t. Okay, mass of the body at time t is nothing but mu minus mu, or initial mass minus mass flow rate into time t. The acceleration at time t will be given by constant force divided by this value, or F divided by m minus mu t is equals to acceleration. And when you integrate this, okay, acceleration is nothing but dv by dt. You also get the relation of v and t. Simple enough. Understood the scenario? Okay. In this scenario, the sand was losing. So in this scenario, okay, the sand was falling off from the car. That means final momentum, the velocity of the delta m mass is v. Okay. Now let's look at this next question. Now this question is same as before. Okay. But instead of masses being added, sorry, instead of masses being subtracted, the masses was being added with mass flow rate of mu. That means 5 kg per second was mass of mass was added to this hopper. Okay. So if a constant force is applied, find out the velocity. Okay. Find out the time dependence of velocity and the acceleration. Okay. The initial velocity out here also is equals to 0. How do I know? See, the mass starts moving. That means initially the velocity of this block or hopper was 0. So what is the equation that I apply? I apply the same equation as this one, isn't it? This is the equation. You just copy this equation and paste it out here. One thing to note out here is, see, in this case, okay, the delta m amount of mass that was used in derivation was being accelerated from zero to final velocity of the hopper. Whereas in the initial case, the delta m mass was means deficit of acceleration. That means it was not accelerated. Okay, and that amount of acceleration was added to the larger block. Okay, or larger tanker. But the change in velocity was from v to dv, no, v to v plus dv. So the change in velocity of this dm drop is nothing but delta v. Out here, change in velocity of this dm drop or delta m drop is nothing but v plus delta v. In this case, the change in velocity of the delta m drop is v plus delta v. In the previous case, the change in velocity of the delta m drop is nothing but delta v only. Understood? Fair and fine. Now see out here, f into delta t. Okay, fair and fine. Okay, so force into dt is equals to m plus mu t into dt plus dm v. Okay, or force is equals to m plus mu t, okay, into, out here I'm writing the equation wrong. Instead of dt dv, delta v gets transformed to dv, not dv. Okay, so I wrote that wrong. So into dv by dt plus v into dm by dt. And if you look at this equation very carefully, force is equals to dv by dt. This entire thing is nothing but dv by dt. Mass into dv by dt plus velocity into dm by dt. Understood? And this dm by dt is given as mu. Okay, mu or 5 kg of mass is being added per second, or mu kg of mass is being added per second. Okay, so I can rewrite this equation as mu into v, mu into v. Now can I send this term to the left hand side? So it will be nothing but f minus mu v is equals to m plus mu into t into dv by dt. Okay, so let's send this dt term out here. mu plus or m plus mu t term below dt and f minus mu v term by below dt. What I'm doing out here is nothing but dt by m plus mu t is equals to dv by f minus mu v. So I'll integrate both sides, and the integration is nothing but integration by substitution. So it will be nothing but ln how much? M plus mu t, m plus mu t divided by mu, divided by mu. I'm directly doing it, okay? Just take m plus mu t as x, okay? Then dx by dt, substitute the value of dt out here. Out here, take f minus mu v as y, okay? dy by dv, substitute the value of dv out here and y out here. So we'll get the equation, okay? I'm just doing it directly to save some time. Out here, ln f minus mu v divided by mu, divided by minus mu, okay? And these are nothing but integrals, okay? Minus mu and out here, these and these would get cancelled. Okay, out here there is a minus. So I must not forget about the minus. The minus was out here, no? I can multiply the minus out here. The lower limit of time was 0, the upper limit of time was t. The lower initial velocity was 0, the upper initial velocity was v. Okay, so I can say that minus, okay, ln, I'm just doing this log part also directly, okay, m plus mu t divided by m plus mu t divided by capital M, okay, is equals to ln f minus mu v divided by f minus mu v divided by f. Okay, if I multiply this minus inside the bracket, it would be nothing but m plus mu t divided by m to the power minus 1. So the entire thing would be m divided by m plus mu t. This entire thing would be m divided by m plus mu t, isn't it? I'm taking anti-log of both sides. Okay, or you can simply say no, m by m plus mu t is equals to f minus mu v by f. Okay, so out here, if I erase this both term, okay, I can send this f to out here. So f can be multiplied out here. Okay, or mu v is equals to, the equation would be f minus mu v is equals to mf by m plus mu t. So f minus mu v, f minus mu v. I have to find out the value of v. So I can send this mu v term to the left hand side and f minus term to the right hand side. So out here my equation would be mu v is equals to f minus mf by m plus mu t. Okay, or divide the entire thing by mu. So I just simplify it. Okay, I just quickly simplify it. Out here I'm simplifying it. Or mu v is equals to, I multiply this term with this term, mf, okay, plus mu tf plus mu t f minus mf divided by how much? M plus mu t, mf gets cancelled. Okay, let's erase this one. Or mu tf divided by mu. Okay, if I cancel out this mu and mu, is equals to ft divided by m plus mu t. Or let's write this as ft. So the equation of velocity is given by ft divided by m plus mu t. Fair and fine. What is the acceleration? Acceleration is nothing but dv by dt. Out here acceleration is dv by dt. So if I differentiate this entire term with respect to t, what do I get? Acha, I have to differentiate it by parts. Okay, so I have to differentiate this entire term to get the value of acceleration. Okay, so instead of solving the acceleration out here, okay, I just solve the acceleration in the next page. Okay, otherwise it will be very cluttered. So velocity is equals to ft by m plus mu t. So velocity is equals to ft by m plus mu t, isn't it? Okay, and acceleration is equals to dv by dt. So acceleration is equals to dv by dt. I have to differentiate it by parts. Okay, so this velocity can be written as f into t into m plus mu t to the power minus 1. Okay, you can consider this as a, this as this. So this is nothing but dft by, or if I integrate, or if I take ft as constant and integrate the m plus mu t to the power minus 2 minus 1, and I have to go inside and differentiate the mu t also. So differentiation of mu t is nothing but mu plus, now I'm taking this m plus mu t as constant and I'm differentiating ft. So differentiation of ft is nothing but f. So if I rewrite this, okay, this m plus mu t to the power minus 2 can be written as 1 by m plus mu t square. So m plus mu t square. Okay, ft into minus 1 into mu is nothing but minus mu ft. So minus mu ft, minus mu ft. Okay, out here m plus mu t to the power minus 1 can be written as 1 by m plus mu t. This can be written as 1 by m plus mu t, isn't it? Okay, and this f and f is we know it. Okay, now see, somehow I have to add these two. So in this parameter, I'll just multiply the numerator by m plus mu t, denominator by m plus mu t, so that both the denominator become same, and you can add these two terms. Okay, so it is nothing but m plus mu t in the numerator and m plus mu t in the denominator. It becomes whole square. Now if I take the LCM, or acceleration is equals to dv by dt, is nothing but the LCM out here is nothing but m plus mu t square. Okay, minus mu ft plus f into m plus f into mu t plus fm plus f into mu t. So minus this and this gets cut. Our acceleration is equals to dv by dt is equals to fm by m plus mu t whole square. Okay, so this is the value of our acceleration out here. Understood the two scenario? The main crux of this problem is impulse provided to the system is equals to final momentum of the system minus initial momentum of the system. Okay, so that was our problem. So in this question, okay, a chain is out here. This is the chain. Okay, let the mass of the chain be m or whatever. Okay, and the chain is dropped out here. No friction is there. What will happen? The chain will slip. Okay, and it will get accumulated out here. The question is asking with what velocity will this end of the chain slip out of the tube. That means when this end of the chain was out here, what was the velocity of the chain? Okay. Now, if I take this entire mass or mass of the entire chain as L, sorry, mass of entire chain as M, okay, and length be L, and length of entire chain, length of entire chain is L, okay. The mass density means mass per unit length. And why do I require this mass density? Because out here, if I have to find out the mass of this much amount, this much part of the chain, okay, this is nothing but mass density into length of this much. If I want to find out the mass of this much amount of chain, mass density into length of this much time. Okay, so mass density, not this much time, this much length. Okay, to understand, no? So mass density is equals to total mass divided by total length, and I'm writing this as lambda. Okay, so mass of this much part of the chain is nothing but lambda into h. Okay, mass is equals to lambda into h. Mass of this much amount of the chain. Okay, this much amount of the chain is nothing but lambda into h. Mass of this much amount of the chain. Okay, let this length be x. Let this length be x. So mass of this much amount of chain is nothing but lambda into x. Lambda into x. Okay, now what is happening? This mass is pulling this block or pulling this mass. Okay, so let's draw the free body diagram. Out here, delta or lambda x amount of mass is being pulled by how much amount of mass? Lambda or lambda h. Okay, and doesn't matter how much of the chain is dropped off. Okay, the height will always be h, so if some amount of chain is dropped off and accumulated out here, okay, will that exert any force out here? No, it won't exert any force out here. No, understood? So it doesn't matter how much of the chain has dropped or how much of the chain has collected out here, this force won't be transmitted out here. That means there won't be any force due to additional chain that is lying on the table. Okay, so the mass out here is always constant, which is equals to lambda into h. This much understood. Whereas the mass out here is variable, because as this chain is sliding off, this amount of mass or this amount of length is reducing and reducing, so the mass is decreasing and decreasing. Understood? This amount of length or this amount of mass is constant, because it doesn't matter how much of the chain is lying on the ground. Okay, that much force or that much mg won't be helping to pull the chain. Okay, the chain lying on the ground won't put a tension force on the chain. Won't put a tension force on the chain. Okay. Okay. So out here, let's say the acceleration out here was a. Okay, even the acceleration out here would be a constant motion. So I'll get two equation out here. T is the tension out here. T is the tension out here. So if I write the free body diagram, lambda h or mg minus t is equals to mass into acceleration. Okay, and if I write this equation, if I write the equation of this body, t is equals to mass into acceleration. Out here, the mass of this body is lambda h, so this mass is nothing but lambda h. So this acceleration would be lambda h into a. Let me write this properly. Lambda h a, and this mass out here is nothing but the mass of this body. This is nothing but lambda into x. Lambda into x. So this mass is nothing but lambda x. If I solve this equation, T and T would get cancelled. Lambda hg is equals to lambda h a plus lambda x a. Okay, lambda and lambda would get cancelled. Okay, acceleration would be equals to hg by h plus x. Acceleration would be equals to hg plus h plus x. This is the acceleration out here. Okay, so the acceleration of the chain out here would be equals to h into g divided by h plus x. Okay, for acceleration at certain time. If you note out here, the value of acceleration is variable. That means the value of acceleration is dependent upon x. So as the value of x is decreasing, the value of x or value of acceleration would be increasing. Okay, fine. But the question out here is asking with what velocity? Because the question isn't asking about the acceleration. With what velocity? Okay. Now somehow from this equation, I get the intuition that I have to find out the velocity from this equation. If acceleration is given, distance is given, x is given, with some complex terms. What is the equation I must use? dv by dt, or a is equals to dv by dt, or a is equals to v dv by dx. X is given out here, no? So out here, the common logical term would be to use a is equals to v dv by dx, isn't it? So if I apply the equation, hg by h plus x is equals to v dv by dx. Now the entire equation becomes simple. hg by h plus x into dx is equals to v dv. I just copy this equation on the next page and solve it. Okay, let me just copy this equation. Copy. Okay, next page. Paste. Pull it up. Okay, so this is the same as integration by substitution, or hg into ln h plus x. Okay, is equals to v dv is nothing but v square by 2. Now I have to put the upper limit and lower limit. Okay, now to put the upper limit at x is equals to x. Okay, initially when the entire length was x, what was the velocity? Let's see, the velocity was 0. See, at certain moment is set free. Set free means initial velocity is equals to 0. Okay, the chain was set free. So at length is equals to x, the velocity was equals to 0. So at length is equals to x, the velocity was equals to 0. Okay, we have to find out the velocity when the value of x becomes 0. We have to find out the velocity. When the entire chain came off the table. That means the value of x is equals to 0. Okay, isn't it? So if I solve this equation, hg into ln h plus or x, h by h plus x, okay, is equals to v square by 2 minus 0. Okay, fair and fine. Or v square is equals to 2gh ln h by h plus x, or v is equals to how much? Under root of 2gh ln h by h plus x. So this was the equation. Okay, so I do know that irodov is equation of irodov are hopeless. Okay, but you cannot disagree with me that the concept of irodov are useless. The concepts of irodov are more on very much essential for your JW advanced kind of thing. Okay, and the equation part, I'm not saying that equation is useless or equation is not necessary. There is no one in the world that can teach you to do equation. Until and unless you practice equation, you cannot get better at it. Doesn't matter how much I show you simultaneous equation. Doesn't matter how much I show you different methods of solving equation. You divide this one, divide this one. You must solve a lot of equation and get the intuition that this is happening out here. So this variable is required out here. So I must somehow get this variable required, this variable out here. These are the equation that I can apply. This equation is happening. These are the equation that I can apply. These are the concept equation I can apply. And in this equation, somehow these variables must come out here. Okay. So the concept and the principles or equation that every physics teacher will give you. But the intuition of developing the variables in the equation, that you have to practice by your own. I can give you for this specific problem, for another problem, for more problems I can give you. Okay. But until and unless you practice that by your own, you cannot develop, or you cannot develop a good skill in physics. Not good skill in physics, good skill in JW physics. Okay. Physics, entire thing, the subject. JW physics is nothing but a combination of good concept and a tough equation. So tough equation you have to practice by yourself. There is no other way. Okay. So in next classes we'll start with some elemental concept of rotation. Okay.